So the topic of vectors is very useful especially when you're talking about forces. We're not quite there yet, but even when we're just describing motion, it becomes very useful to talk about vectors, especially when you are adding velocities which have a speed and a direction. So again, when we draw a vector is a fancy name for an arrow. And the length of the arrow represents the magnitude. And then, of course, the arrow implies the direction. So velocity as a vector can be represented as vectors. Accelerations can be represented as vectors. And forces can be represented as vectors. That's what we're going to be doing a lot of. But even simple things like the direction a man walks. He walks 5 paces to the east. That's a vector. 5 is the magnitude, and east is the direction that he walks. So vectors are very useful in solving problems that involve velocity, acceleration, and force. So for example, I'm going to ask you to do one of these problems for yourself in just a minute. But in terms of one-dimensional speed problems, in one dimension, let's say we have an airplane that is traveling 500 miles an hour to the east. So let's represent this arrow. Let's see, 1. Let's make that a 1. Make this a 2. Make this a 3. Make this a 4. Make this a 5. Okay? So 1, 2, 3, 4, 5. That's a big vector. So we have an airplane that is moving 500 miles per hour east. Okay? Let's say we have wind that is moving 100 miles per hour. So I've drawn my vectors. So the scales are, we have scale here, right? That this is 5, then this is 1. That's why I use that to mark off 5. So when you're working on your graph paper, you can go 5 squares and 1 square. Okay? So when you're flying, you can be flying at no wind. You can be flying into the wind, or you can be flying with the wind, right? When you're flying into the wind, it's called starts with an H, ends with a wind, headwind, right? When you're flying with the wind, starts with a T, tailwind, right? So you either have a headwind or a tailwind. And sometimes you've been on the airplane and the pilot just says, yeah, we're cruising along at 500 miles an hour, but we have a headwind of 100 miles an hour, right? So there is wind blowing us back, and so we're not making as much headway as if there were no wind, right? Because we're being blown back a little bit. Well, what I want to show you is the head-to-tail method of vector addition. So we're going to use vector addition, the head-to-tail method, to solve this problem. So the question is what is the ground speed of the airplane? Most of you have already figured it out. Well, I'm going 500 miles an hour and I got a 100 mile an hour headwind. I must only be going 400 miles per hour. Okay? So this is good. You know that. You didn't need vectors to come up with that answer. But let me show you that if you put the head of this vector onto the tail of this vector and you orient those vectors in the proper direction, then what we call the resultant vector, so we're adding them, but since this is going in the opposite direction, we're actually subtracting. The resultant vector is 1, 2, 3, a vector of magnitude 400 going that way. So this is my initial 500 east. Then I put head to tail, 100, the wind's going to the west. And so the resultant is 400 east. So this is a one-dimensional problem that we have solved using vectors. Now, as vector addition is very powerful, we can apply it to multiple dimensions. And a classic example is the boat crossing the stream. So now let's look at a two-dimensional problem. And let's say that we have a boat. Here's a boat. And it's got a little motor on it. Here's a motor. And it's headed across the stream. Right? It's got a little weight going behind it. As far as the motor is concerned, we're pushing the boat with a vector of, I'm going to draw my vector. Let me draw my vector. I'm going to say let's say 20. Why did I do that? So as far as the motor's concerned, it's clicking along at 20 meters per second. But it's a river. And the river has a current associated with it. And the current of the river, so this is the boat, and this is the current, is, say, 10 meters per second at 90 degrees to it. Right? So I don't want to have, if we're saying that this is north, then the current is going to the west. Right? So the boat is going north, because this is a vector, and the current is going west. Okay? So here's our two vectors. So you didn't need vector addition for you to analyze this problem, and you know that if you're in a boat going across the creek and there's also a current blowing you across, what is the net result of the motion of the boat? Do you head straight north? Do you head straight west? You go a little bit of both, right? So how much, you can now quantify this if you use vector addition. Using the head to tail method, you put the second vector's tail onto the head of the first, and you get a resultant vector. So now the resultant vector, I'm going to draw in orange, using the head to tail method, is the direction that you're going, right? So if the current was 10 going to the west and the boat was going 20 towards the bow, then the net result, the resultant, and this is, make sure you write this word, the resultant vector. The resultant vector is, it's actually a little bit more than 20, isn't that right? Because the hypotenuse is always a little bit longer than either of the legs, right? So maybe the resultant, I don't know, is 22 meters per second in this direction. Okay? All right, so this is a two-dimensional problem. This is a two-dimensional problem that can be solved using vector addition. The third problem that I want to expose you to, yep?
Okay, I don't understand how you got 20.
Okay, I'm just guessing, and then I did a little bit better than guess. This is my 1 unit, or this is 10 meters. This was, the diameter of this little thing was 10. And I used it to measure 20 for the boat and 10 for the current. And then I used this as a little ruler, and I went it here, and it was a little bit more than 20, which makes sense because this is actually a triangle, a 20, 10, something triangle. So actually maybe I could plug this into a calculator and say that C is equal to the square root of A squared plus B squared, since this is a right angle. And I think using Pythagorean theorem, we could come up with the magnitude of C. So let me say this in big boy science terms. We can calculate the magnitude of the vector by applying the Pythagorean theorem, right? Right. Okay, good question, and that allowed me to elaborate on that. Okay. The third problem is, I want to talk about displacement and distance. So last class, well, it was a class before last, and when I talked about displacement and distance, I walked around the room and I said 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I've gone a distance of 11, but my displacement is 0. Right, so we covered that. Now, vector addition is very useful when you're trying to figure out what the displacement is. Let's say a man travels up north, then he travels east, then he travels north again, then he travels east, then he travels south, then he travels east, then he travels south. Right? Then he travels west, then he travels south. Okay? Maybe this circuitous route. Maybe this is 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. What distance has he traveled? 1, 2, 3, 4, 5, 6, 7, 8, 9. What's his displacement? The magnitude of the resultant vector. That is the displacement. The way you would have to find that out is you'd have to measure it. Unless you knew what this angle was. In the other examples, because there was a 90 degree involved, we could use Pythagorean theorem. But if this ends up to be some angle that's not related to a 90 degree triangle, then you would have to measure it. And what I tell my students is if you're doing this on graph paper, then what you would do is you simply take another piece of graph paper and put it along the line and count squares. And that would be the easiest way to find the magnitude.
Squares, that would be like 1 foot.
Well, so if you drew this on this paper, right, and you wanted to know the length of this line, then I would get a second piece of graph paper and put it up here and then count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 30. Right.